So today we're going to start talking about three-phase circuits. So let's call this an introduction to three-phase circuits. All right, so in most industrialized countries, like here in the United States, most of Europe and all of that kind of good stuff, electrical distribution from utilities like power plants to consumers, whether that be a commercial retailer, a home, or an industrial site, is accomplished using a three-phase distribution system. Okay? So what we are probably more familiar with is a single phase system, which is actually what we see in our homes. So a single phase system is going to look something like this. Where we're going to have some voltage source. So this is going to be an RMS phasor. So we're going to call this VP with an angle of theta V, where VP is the RMS magnitude of our phase voltage. I'm going to put some terminals here. Then we're going to have wires, which may or may not have some associated impedance. All of them will really have an associated impedance, but it kind of depends on whether the wire is long enough for it to actually matter. And then on this side, we're going to have a load. So I'm going to subdivide this system up into distinct parts. Okay. And I'm going to do that by just putting these dashed lines here to kind of show what the different parts are. So over here on the left-hand side, we have the source portion of the system. So there's a couple of different ways that we could actually think about this source in the context of a single phase system. So it very much could be an outlet like we have over here. But a more true representation of this would actually be effectively the service panel in your home, right? Your load center or something like that. That's where your electricity actually comes in from your external sources and gets distributed among all of the circuits in your home. So this would kind of be representative of like one circuit that's connected to a single breaker, okay? So we have the source side of things on the left-hand side. In the middle, we have what I am going to call transmission lines. In a single phase system, we typically have a single hot wire for each circuit and a single neutral wire for each circuit. And then over here on the right-hand side of things, we have our load, which is just something that we kind of plug into our receptacle. So that could be representative in a home setting of like a heater or a computer or an oven or something like that. Okay. So I'm going to use a notation that's going to help us understand what different quantities mean when we're looking at things. So on the source side of things, I'm going to typically use lowercase letters. So I'm going to call this terminal here terminal A for our hot wire, and the lowercase a is for the source side. And then I'm going to put an uppercase A over here on the right-hand side to let us know that we are on the load side of the transmission line. And I'm going to do something similar here. I'm going to have a lowercase n on the source side for our neutral wire, and then an uppercase N on the load side for our neutral wire, okay? So all of the time we're referring to anything on the source side of the system that's going to be dealing with lowercase letters. Anytime we're dealing with anything on the load side of the system, we're going to be dealing with uppercase letters. So it's an easy way to differentiate what quantities and all of that kind of stuff that we're going to be looking for. All right. This is a basic overview of a single phase system. The only thing that I have potentially left out of here would be that our hot wire and our neutral wire may have some impedance as well, and we'll get to that in a little bit. Now let's look at an example of a three-phase system. Okay. We're going to break it down similarly. So this is what's going to be a three-phase, three-wire system. This is just one example of a way that a three-phase system can be realized, of which there are many, many different ways. Okay. So just like in our single-phase system, we're going to put all of our sources on the left. Okay. So this is going to be the A phase terminal of our three-phase source. Here's our B phase terminal, or B terminal of our three-phase source. And here's our C terminal of our three-phase source. And I'm going to put the positive polarity connected to those terminals. And all of the negative polarity terminals will be tied together. And so this voltage will have some RMS magnitude and some angle, we'll call it theta A. Let's do lowercase a since we're on the source side. We'll have the same magnitude, typically angle B, and the same magnitude angle C. We're going to have our transmission line network. So this is the A conductor. So it's a hot wire. Right here, we're going to have our B conductor. And down here, we're going to have our C conductor. This particular system does not utilize a neutral wire. Some will, some won't. Kind of depends on the application, and we'll talk a little bit about that. And then over here on the load side, I'm going to put in a three-phase load. So let's call this ZLA, ZLB, and ZLC. And I'll put those dashed lines just to show that we are dividing this up into the same three distinct parts, right? We have our source on the left, our load on the right, and then we use transmission lines to connect our source to our load, or vice versa. So let me ask you guys a question, which probably don't know the answer to, but I'm going to ask it anyway. Why is power typically distributed in three-phase systems on a large scale? So for what it's worth, the single phase system that we have here, which is representative of something like that we would have in our phone or in our office building or anything like, or excuse me, our home or our office building or anything like that, is usually part of a three-phase system. We just have access to only a single phase. So to say that a three-phase system gives better or more stable power than a single-phase system in most contexts really can't be true, because the single-phase system is part of the three-phase system itself. We just don't see the other two phases. So let's say that the magnitude of our source voltage there, VP, is literally the exact same thing as the magnitude of our three-phase source voltages. And the impedance of our impedance ZL is the same as the impedance of our three-phase impedance, ZLA, ZLB, and ZLC. Notice that in our single-phase system, it requires two wires to deliver some amount of power to our load. In our three-phase system, it requires three wires total to deliver 3 times as much power to our load if all of our source voltages are the same and all of our load impedances are the same. So it takes 2 wires to, let's say, deliver 1 kilowatt of power, or 3 wires to deliver 3 kilowatts of power. A three-phase system is actually cheaper in the long run. It's less infrastructure costs because it requires less wires to carry significantly more energy. Okay? So that's one of the biggest reasons why three-phase systems are used to distribute power, especially over long distances. It lowers the infrastructure costs associated with transmitting that power. Charlene, what's up?
You have flexibility with your load.
For sure. So the example that I have right here, and we'll talk about this in a little bit, is what would be considered a Y connected load. We could also have a delta connected load. We could also add single phase loads to this and all of that kind of stuff as well. And even for those single phase loads, we have a choice between whether we're going to put it between the A terminal and a neutral terminal, or between the A and B terminal. So there is a lot of different permutations of ways that we can connect things, right? For a three-phase system, what we're going to find in practice is that, so let me explain it this way. So I work for a company outside of Louisiana Tech called Sabre Industries out in Bossier City, Louisiana. And one of the things that I help them do is designing effectively, like we make large scale battery energy storage enclosures. I do some of the design for that, and some of that design entails effectively making the power schedule for that. And so let's say that we have a site where we're going to put 42 units, like 42 large containers out there. And each one of those large containers is going to have a three-phase HVAC unit. Well, that three-phase HVAC unit is kind of a misnomer because the compressor is actually a single-phase load. Okay. So part of my job is to go through the system and say, hey, for every third unit, we're going to connect that compressor across the A phase, and then the second unit and every third one after that is going to be across the B phase, and then the third unit and every third one after that is going to be on the C phase, so that overall the entire system looks balanced. So we can connect those single phase loads across different phases in order to balance the system out. So we know that some of the buildings might have a heavier lighting load than others, so we tend to distribute those in order to balance everything. So a three-phase system in general does allow us a lot of flexibility in order to try to keep things as balanced as we possibly can. So that's definitely a thing. Another reason why three-phase is used in a whole lot of industrial applications, and we'll see this in a couple of days, is the power and torque that are generated by a three-phase source is effectively going to be a constant value. So even though we have 3 sinusoidally varying voltage sources, we are going to generate a constant torque to any rotating electrical machine. What is an advantage of having constant torque for our rotating electrical machine or constant power delivered to our rotating electrical machine? So if the power surged, right? So if the power was constantly changing, what do you think the motor is going to do? It's going to vibrate because the power is constantly changing. But if we can have a system where the power delivered to it is constant, it's not going to be undergoing constant changes in speed. It's not going to vibrate or anything like that. It's going to have a nice, safe, stable operating point, which is the reason why three-phase induction motors last forever. They're built very robustly for very hazardous environments, but a large part of that robust building is coming from the fact that we don't expect them to undergo significant vibrations really ever, as long as they're delivered a consistent amount of power. We have three-phase motors down in Neskin Hall that are World War II era, and we literally still use them for research and lab experiments, as Ron can attest to, because they just won't die. All right, so we've kind of talked about the why to some extent of three-phase systems. So now let's talk about how things work. So you're going to have to bear with my terrible drawing skills here, especially when it comes to concentric circles. Okay, so let's call this bit right here three-phase voltage sources. And we are going to do a very, very surface level look at what is effectively a synchronous generator here. And we'll talk about it in much more detail in your next power class, specifically on electromechanical energy conversion, which is exactly how these guys work. Okay. So this is a scaled down / simplified look for sure. So bear with me while I shittily draw a couple of circles. So this structure here is what is called the stator. And that simply means that it is the stationary part of a rotating electrical machine. So the stator is built with coils of wires effectively embedded into it. So I'm going to put one thing right here that corresponds to one coil of wire. And so this is effectively, we're going to think of it kind of like a send path. So this is going to be for our A phase conductor. So I'm going to put a little A here. And then exactly 180 degrees across the stator, we are going to have the return path, which I'm going to call A prime. So send is A, the return path for the current is A prime. I'm going to fill that in gray. We'll talk about why that is in just a moment. So physically, 120 degrees out of phase with the A coil will be a B coil. Typically, this is blue, or I say typically, but for 12208, this is blue, which is the three-phase power that we have access to in this building. And then 180 degrees out of phase with the B coil is going to be B prime, and I'm also going to color that one in gray. and then 120 degrees out of phase with the A and B. So over on this side, we are going to have our C phase coil. So here's its send. And here's its return path. So let's call this C and C prime. And we're going to wire things up like so. So this is the A terminal of my source. Here's my B terminal. Here's my C terminal. And then all of those return paths would typically be connected together. Like so. So we have these three electrical terminals to deal with on our stator. And then here in the middle, I'm going to put our rotor. And I'm going to represent the rotor as if it were simply a permanent magnet with a north pole and a south pole that was mounted on a pin here in the middle that allows it to rotate. And we would use some sort of mechanical action, typically called a prime mover, to rotate this rotor at a particular angular frequency, omega. So we spin that rotor around, we put mechanical energy into this system, spin that rotor around. Have you guys had any electromagnetic field theory stuff? Okay, so what happens when the flux passing through a coil is changing? You're generating a voltage. Absolutely right. And so that's exactly what we're going to see here, right? So we have this permanent magnet that's passing flux through these coils. And as the magnet spins, the flux through each individual coil is going to change, which is going to cause a changing voltage generated between the A and neutral terminals, the B and neutral terminal, and the C and neutral terminal, effectively for each phase. So mathematically, it should look something like this. And now we are relying on my ability to draw sinusoids, which is equally bad as my ability to draw these circles. So the A phase I did in black. So let's say that this is our peak value here. So it might look something like this. I didn't give myself enough room to do a full cycle. So let me send that a smidge. So the black curve is what we'll call VAN, sorry, of T. And it'll have some value. So let's call this VPA times the square root of 2 cosine omega t. And we're just going to arbitrarily assign the phase angle for the A phase here to be 0 degrees. I'm using that square root of 2 there so that when I talk about RMS values for all of this in a moment, it'll literally just be VPA. All right. So that's what's going on with our A phase. So if that's what our A phase looks like, what do you think our B phase should look like? Should be effectively the same thing, except that it's going to lag the A phase by exactly 120 degrees because the magnet has to move 120 degrees in order to be fully aligned with the B phase of the coils, right? So it should hit its peak value roughly here. And that would mean it'll hit its negative peak about there. So something like that, where this blue curve would be VBN as a function of time, will be VPB root 2 cosine omega t minus 120 degrees volts. Sorry, let me use units. And the red, or the C phase, which is in red, is going to lag the B phase by another 120 degrees because of the physical 120 degree phase separation between that coil, right? So that would mean that it should hit its peak about right here. Something like this. So we have 3 sinusoidally oscillating voltages. And they are all 120 degrees out of phase with each other. We call this a positive phase sequence. Okay. So in a positive phase sequence, A hits its peak first, then the B phase, and then the C phase. A negative phase sequence it would go C hits first, then B, then A. How do you think we would achieve a negative phase sequence? We would simply spin the motor in the other, spin the rotor in the opposite direction. And that would make, instead of B lagging A by 120 degrees and C lagging B by 120 degrees, we would see that C leads B by 120 and B leads A by 120. Effectively would have this exact same system, but the signs on our phase angles would be opposite. That's all that would change if we spun our motor in the opposite direction. And because that's the only change that we would see, we are going to deal exclusively with positive phase sequences in this class, with the understanding that if we just change the direction of rotation, we have a negative phase sequence system. Okay. So this is how three-phase voltages are generated. So let's talk about a couple of things here really quickly, okay? The phase angle between the phases is always going to be 120 degrees because our coils are physically located 120 degrees away from each other, okay? So that is a fixed thing, okay? If we know the A phase, we can immediately know what's going on in the B phase simply by subtracting 120 degrees from the phase angle. We can know what's going on in the C phase by subtracting 240 degrees from the phase angle. So we only ever actually have to care about what's going on with the A phase as far as the phase angle is concerned. Now let's talk about these VPA, VPB, and VPC quantities, okay? As long as the number of turns in each coil is the same, those voltages are also going to be the same, right? So as long as our motor, or excuse me, our generator is manufactured correctly, it should be. There's a reason why these are built by robots with extremely low tolerances, or I guess high tolerances. Whatever makes them extremely identical to each other. We are going to see that the variation between these phase voltages is going to be incredibly small, on the order of millivolts, when we're talking about hundreds of volts being supplied by these things, okay? So for all intents and purposes, VPA, VPD, and VPC are literally going to be the exact same voltage. Okay. So from an RMS standpoint, this means that we are effectively going to have 3 voltages. So we'll have an RMS voltage VAN that's just going to be VP angle 0 degrees, volts RMS, VBN, which will just be VP angle negative 120 degrees, volts RMS, and VCN would be VP angle negative 240 degrees, volts RMS. So those are what our RMS phase voltages for the source will usually be. All right. So now let's go more into the details about the different permutations of things that we can connect, right? So realistically, we can lump things into 4 basic circuits, okay? So we're gonna have a Y-Y circuit, a Y-delta circuit, a delta-Y circuit, and a delta-delta circuit. And we're gonna talk about effectively each of those permutations here a little bit. So let's call this section source and load configurations. And while we are going through this, we're going to add some definitions in. So let's first talk about a Y connected. We usually see this as just the letter Y, but sometimes you might see it spelled out as WYE. Source. Okay. So I'm going to draw this in 2 ways. One is the way that you will see in the overwhelming majority of textbooks, and I absolutely hate it. And then another way is a way that you will see in a handful of textbooks that I find significantly easier to deal with. Okay, I don't mind whichever one you prefer to use, but I'm going to wind up using the second form because it's easier to draw, and for me, it's easier to understand what's going on. So the classical representation is going to be something like this. So I'm going to put a voltage source here on this diagonal like so. Another voltage source here on this diagonal. Oops, that should be negative. And this is going to be my A phase terminal. Here's my B phase terminal. Here's my C phase terminal. And then in gray, I'm going to put my neutral terminal. And I put it in gray because it's technically optional. We won't always have access to that neutral phase terminal. We will always have access to the A, B, and C terminals. So the purpose of a neutral conductor is to carry imbalance so that your phase conductors don't have to. So effectively, the presence of a neutral allows you to size your phase conductors slightly smaller than they would otherwise have to be, which is going to save money. Now, if you know that your system is effectively fully balanced or extremely close to fully balanced, and so you don't really have to worry about overtaxing or overheating your conductors, you don't need a neutral at all. Also, as we'll see in a couple of moments, when you have a delta configured source or load, there is literally not a place to put a neutral conductor in. So a neutral conductor is only physically exists when we have a Y connected system, which will not always be the case. So if it's there, sure. But if it isn't there, it will just flow through the conductors. And when I draw out a full system, it'll be a little bit more obvious as to why that is. Okay. So I'm going to put my voltage VAN between the A terminal or across the voltage source that exists between the A terminal and the neutral terminal. This voltage right here is between the B terminal and the neutral terminal. So I'm going to call this VBN. And let's call this guy VCN here, because it's between the C terminal and the neutral terminal. So this is the classical representation. And then over here on the right-hand side, I will draw the modern representation, which I've actually already drawn for you guys. So here's VAN, VBN, VCN, and down here on the bottom is our optional neutral. So now let's define some things. And this is where the language and the jargon can start to get confusing and at times overwhelming. So I'm saying that to recognize this is you guys' first exposure to this. It is perfectly understandable for you guys to have questions. I'm happy to answer them and all of that kind of stuff if this is confusing, because it definitely can be. But here in roughly a week's time, it's kind of necessary for you guys to have this jargon sorted out, because if you don't, you're just going to be wildly lost for the next month. Okay. So I'm going to try to explain this as clearly as I possibly can. So the first terminology that we're going to introduce is one that I've already accidentally used, and that is a phase voltage. So a phase voltage is defined to be the voltage drop over one phase of a source or a load. So in this Y-connected voltage source, our phase voltages are literally just the voltages VAN, VBN, and VCN. So it's just the voltage that's provided by the source. That's all a phase voltage needs to be. Now, you may occasionally, in practice, hear these voltages, VAN, VBN, and VCN, also referred to as line to neutral voltages or phase to neutral voltages. I'm not going to use that terminology because there are certain configurations that literally won't have that. So I'm always going to talk about things in terms of phase voltages, and what we're going to talk about in a moment is line voltage. A phase to neutral or a line to neutral voltage is just a voltage that's measured between a phase conductor and the neutral conductor and so forth. So it's nothing particularly difficult to understand. I'm just not going to use that particular terminology because it can get awkward. So the next thing that I want to talk about is a line voltage. So a line voltage is a voltage drop across the transmission line terminals of a source or load. So we define these in a particular order. We'll talk about that here. I'm going to label these in green, and I'm going to try to be consistent with my colors throughout. Okay? So here's my transmission line terminal A. Here's my transmission line terminal B. So I will have a line voltage VAB like so. So whenever I just measure the difference between the difference in potential between my transmission line terminals, that's what's giving me my line voltages. Okay? So measured between the B terminal and the C terminal, so skipping over the neutral terminal effectively, we're going to have a line voltage VBC. And similarly, we can measure a line voltage from the C terminal back up to the A terminal that we're going to call VCA. These are our line voltages for our classical representation. Now I'm going to put them over here. So we'll talk about that in just a moment. So this will be VAB, VBC, and VCA. Okay, so it was asked, why did I seems randomly choose for the line voltage VCA to have positive polarity on bottom and negative polarity on top? The reason why I chose it in that particular way is because if we were to write a Kirchhoff's voltage law equation around, let's do this loop here. So I'm going to do a little bit of math earlier than I intended to, but that's perfectly okay. But we'll find, actually, let me write things here really quickly. So this is VAB, VBC, and VCA. Now I'm going to put a line here because this is technically an aside, but we're going to take care of it now. So if I write a Kirchhoff's voltage law equation around that loop, what I'm going to find is that my voltage VAB will be equal to VAN minus VBN. Let's make sure everybody can see why exactly that is, right? So if I go from the positive polarity terminal of that voltage VAB, that voltage will be equal to the voltage drops that I see. I see the positive polarity terminal of VAN first, so that's why it gets a plus sign. I see the negative polarity terminal of VBN first, so that's why it gets a minus sign, okay? We are going to stumble into a transformation here, but it'll be okay. So we know that VAN and VBN are related to each other, right? So what I mean by that is VAN is VP angle 0 degrees nominally. And VBN is VP angle negative 120 degrees. I can figure out what that's going to be. And that's going to be the square root of 3 VP with an angle of negative 30 degrees. There's going to be positive 30 degrees. Now I'm doubting myself. I'm 97% sure it's positive. Let me sort that out just really quickly. So 1 minus 1 angle negative 120. Yep, root 3 angle positive 30. Sorry for the accidental minus sign first. Now, we could say, doing something similar, that VBC should be VBN minus VCN. Just so we're clear here, let's detail what that path would look like. So we would start here. We see the positive polarity terminal of VBN first. We see the negative polarity terminal of VCN. We come out over here. Right? So that's going to look like VP angle negative 120 degrees minus VP angle negative 240 degrees, which is going to come out to be square root of 3 VP angle negative 90 degrees. So we can see that our line voltage, our B phase line voltage effectively, VBC, is 120 degrees lagging our A phase line voltage. Well, by expressing VCA where the positive polarity terminal is on bottom and the negative polarity terminal is on top, effectively we're doing Kirchhoff's voltage law around this path. So we're going to start here. So we're going to see the positive polarity terminal of VCN first. Then we're going to see the negative polarity terminal of VAN, like so. And so that's going to be VCN minus VAN, or VP angle negative 240 degrees minus VP angle 0 degrees. And that's going to be root 3 times VP angle negative 210 degrees. So effectively, this was a very long way of proving that by putting the negative polarity terminal for VCA on the A side of things, which by the way, that's how the double subscript notation works. And we'll talk about that, I guess, in a second, so that was clear. This makes sure that our line voltages are exactly 120 degrees out of phase with each other, and they obey the exact same rules as before. So the B phase is lagging the A phase by 120 degrees. The C phase is lagging the B phase by exactly 120 degrees. So if we start monkeying around with the polarities of our voltages, all of those fundamental relationships about things leading and lagging by exactly 120 degrees are going to fall apart. So this actually is going to wind up making our life much easier because everything will always be exactly 120 degrees out of phase. Doesn't matter if we're looking at line voltages or phase voltages. We'll see that consequence of labeling things this way is also going to make what are called our line currents and our phase currents all behave in the exact same way, where the B phase will lag the A phase by 120 and the C phase will lag the B phase by 120 degrees. So consistency in the notation is incredibly important to make sure that all of our relationships behave the way that they're supposed to. I'm not sure that I fully understand your question. Correct. Well, so it's not physically changing the phase, it's just the way that we're looking at it is going to make the math more difficult effectively. So let's talk about this double subscript notation thing that I'm using here, because it's also going to tell us effectively where our positive polarity and negative polarity terminal have to be. Right? So the first letter in our subscript is always going to be the positive polarity terminal. And the second letter in our subscript is the negative polarity terminal of that notation. So whenever I say VCA, I don't really even need to put the positive polarity terminal at C and the negative polarity terminal at A, because VCA by itself inherently is supposed to tell you the positive polarity terminal is on the C side and the negative polarity terminal is on the A side. I'm being redundant here just for clarification's sake, because you guys aren't super used to that yet. But a double subscript notation, like we're using here, we're going to consistently use in all of our three-phase circuits, inherently has a specific positive polarity terminal on the first subscript location and a negative polarity terminal by the second subscript. Brock, you good? You look okay. So we've talked about phase voltages and line voltages, and I'm going to delete all these crazy colored things here so we can talk about other quantities really quickly. Oops. I did not mean delete that green dash down here. Okay. All right. So now let's talk about phase currents. So a phase current is simply the current flowing through one phase of a source or load. So here is where I particularly do something that's kind of odd. Okay. On our source here, I am going to define our phase currents as if they're flowing into the positive polarity terminal. So this will be a phase current IAN. This will be a phase current IBN. And this will be our phase current ICN. I'm choosing to do this, even though it is opposite of what practically every textbook I've ever read does, simply for consistency's sake. So we're always going to define our phase currents as currents that are flowing into the positive polarity terminal of one phase of our source, or the positive polarity terminal of one phase of our load. Okay, just for consistency's sake, usually you see textbooks defining them flowing out of the positive polarity terminal for our sources and into the positive polarity terminal for our loads. In the grand scheme of things, it literally doesn't make any difference at all. It just looks like our source is absorbing power and our load is absorbing power, but we know that absorbed power is just the negative of supplied power. So it's not any particular big thing. I just want to point out it is something slightly different that I do when I teach this material. Okay. So representing these phase currents on my modern diagram, we would have IAN, IBN, and ICN, like so. Now, another reason why I define them in this particular way is because of the double subscript notation. So for currents, we're going to take this double subscript notation to mean our current starts at the first subscript terminal and it's flowing to the second subscript terminal. And that will always be true with this double subscript notation, right? So ICN means that current is flowing from the C node towards the neutral node. IBN means it's flowing from the B node towards the neutral node, et cetera, et cetera. So it's just going to make everything consistent and everything easy to understand what directions we're expecting things to flow, and it'll all be consistent, regardless of whether we're looking at the load side or the source side. So those are our phase currents. So IAN, IBN, and ICN. And the last terminology that I want to introduce here, and I'm screwing it up already, is what are called line currents. Okay. So line currents are nothing more than current flowing through the transmission line from source to the load. Now, I can't, let me scroll back up so you can finish writing that. Sorry. I can't represent line currents on our source because we don't have anything connected, right? If I scroll back up to our original picture that I drew though, we'll come up here, we would have a line current IAA, like so. So it's flowing from the source side transmission line terminal to the load side transmission line terminal. Here is our line current IBB. And this one's getting kind of busy. Here is our line current ICC. So line currents are always just the currents flowing down the transmission lines. Pretty simple to understand. So these are the four signals that we're going to be dealing with and sorting out for every possible configuration of source and load. Okay? Phase voltages, just to recap, are simply the voltage drop across one phase of our source or load. Line voltages are the voltage measured between the transmission line terminals. Phase currents are the currents flowing through one phase of the source or load, and line currents are the currents flowing down the transmission lines. All right, so how okay are you with a Y-connected source and understanding of phase voltages, line voltages, phase currents, and line currents? Everything seems relatively okay right now. Now we're going to look at a delta connected source, and you're immediately going to be pissed off. So, a little too far. All right, so we're looking at a delta connected source now. So I will again first draw this in a conventional or traditional way. I can't remember what classic, I think is what I called it a moment ago. Let's wrap this over here. So this will be our A, B, and C terminals. So we're going to have some voltage VAB like so, some voltage BBC like so, and then some voltage VCA like so. So this is our classical representation. And then over here on the right-hand side, I will draw in our modern representation. So that's all. And from a fundamental definition of something being in series or something being in parallel, neither case satisfies that criterion of the voltage sources being connected in series or the voltage sources being connected in parallel. So effectively, for the Y-connected source, we connected all of the negative polarity terminals to one common neutral node. Here, we are connecting the negative polarity of the A phase to the positive polarity of the B phase, the negative polarity of the B phase to the positive polarity of the C phase, the negative polarity of the C phase to the positive polarity of the A phase. So that's really what's going on. It's kind of a cyclical thing versus having a common reference point. But in neither case are the circuits, or are the voltage sources connected in series, nor are they connected in parallel. Mm-hmm. 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 So let's do something. Let's take a quick aside here. I'll come back to this in a moment. And let's see what would happen mathematically if we connected all three voltage sources in series. Okay, I'm going to do this on page 12. So let's say that I had, so this is VAN. You guys don't need to write this down. We're just doing a thought experiment here because I want to prove something. And Brock is going to get annoyed, but it's okay. Yeah. So here's VAN, here's VBN, and here's VCN. Let's say that we put them all in series where we're just using this as some phase angle, there's going to be some phase voltage magnitude with an angle of 0 degrees. Here's that same VP with an angle of negative 120. And here is VP with an angle of negative 240. And we wanted to know what this voltage is here. The voltage drop across those three sources if they were connected in series. So Rock, get your calculator out for me. Let's just say, for the sake of argument, that our phase voltage magnitude is 1. So I would like you to put in your calculator what 1 angle 0 degrees plus what angle negative 120 degrees plus 1 angle negative 240 degrees is, and tell me what result you get. So you typed it in incorrectly. You should get a finite number, perhaps a surprising result. Yes. Well, if they were all of the same angle, then you would just get 3 times the magnitude with the same angle. But how can you get the same angle when our coils are physically located 120 degrees out of phase with each other? But that's, so you're saying if we connected multiple 3-phase sources in series, like 3 phases collectively, and then string those in series, I dare you to explain how you would wire that up. But so you're saying if we wired up 3 single phases in series, well, yeah, but that's an entirely different bag of cats because we're talking about 3-phase circuits.
I understand what Ronald's trying to say, but couldn't you, in that, when they didn't do
Yeah, you would make the coils have 3 times as many turns to generate 3 times as much voltage or something like that. Yeah. If you want more voltage, you use a physically larger source. You don't add multiple sources together. Yeah. Sorry, go for it. So let's put a pin in that until we actually get to looking at our power analysis, but it will be exactly 3 times the power. And I think middle of next week, we'll have that sorted out. I'm not trying to pick on you, and I hope you don't feel that I am. I understand that this stuff, especially when you're first seeing it, is ridiculously confusing. Sure. Well, realistically, we are not wiring it differently. We are provided with a system that is wired in this way. I mean, you might go work for a generator manufacturer or something like that. But anyway, yeah, so this is just 2 different ways that a generator effectively, or a 3-phase voltage source, which could be a generator, it could be the secondary terminals of a transformer, or whatever is capable of supplying voltage to a load. It's just 3 different configurations that they're wired in. Or it can be 2 different configurations that they could be wired in. Yes.
This allows power factor to.
So jumping ahead, no, it's fine. So jumping ahead, it is a similar process in as much as it's just going to involve the placement of capacitors. However, instead of using a single capacitor, you have to use a capacitor bank. And that capacitor bank could be connected in a delta configuration or a Y configuration. And there are advantages to both. So we're going to be doing effectively all of the same stuff that we did for single phase circuits in a 3-phase system, and see what adaptations need to be made in order to carry out that same. Yes. You don't get three phases out of one. So let's go back to the voltage source that we physically drew here, right? So I have, so this would be what's called a three phase, so this would be two pole. Right. So I have a total coil between the A and the A prime, right? So effectively, a current flowing into A, current is flowing out of A prime. So that completes effectively one total loop for that phase of the current. Current is flowing into B, out of B prime, and so forth, right? And so because our coils are physically separated by 120 degrees of phase, we wind up getting three voltages that are separated by 120 degrees in phase. If instead, and I don't want to get too wackadoo with things yet, so this is a three phase and this is a two pole motor because each coil has its own effectively positive polarity terminal and negative polarity terminal denoted by the not prime and prime. We could actually do 4 poles and 8 poles and all of that kind of good stuff. And what we would find is that our mechanical frequency omega and our electrical frequency are going to be different. They're going to be related to each other based on the number of poles that we have, which is a problem for power too. We'll talk about that more in depth. But effectively, how I have things drawn right here is the simplest possible case where it takes 120 degrees of rotation to go from the A phase to the B phase. But I could have multiple A phase things around here, multiple B phase separated by different angles. And the mechanical angle is going to tell us what the electrical angle is going to be. And or the total distance traveled mechanically is going to define what our electrical angle is. And that's a problem for the next class that we have. No. So a DC motor, you only have a DC voltage as an input. You have to have a thing called a commutator, which is used to effectively switch the direction of the current constantly so that the motor doesn't turn like this and then like this back and forth over and over and over again. The more pieces that you have or you divide your commutator into, the more smoothly the motor spins. Because if you just have a single commutator for positive and a single commutator piece for negative, it's going to act very jerkily because the voltage that's applied across the terminals is constantly experiencing a very large change. Whereas if you break your commutator up into like 60 pieces, it's going to see a small ripple. So that I know of, I want to say the highest that I've heard of would be a 12 phase system. So you might use higher phase systems and all of that kind of stuff, like in metal refineries and all of that kind of jazz they use.
Sorry. I didn't draw, so I'm going to put this on my house.
Mhm.
Will I feel any like three or one thing?
All you will be dealing with is three phase systems. I don't know if that is a fist shake of victory or defeat, but anyway. a little of both. Okay, yeah. So if you have an internship with an electrical utility here in the United States, you're guaranteed you're going to be dealing with three phase power.
Is there no
Yep. All right. So I'm now going to get back to drawing the modern representation of this delta connected source 15 minutes after I started. Let me draw this damn picture, please. So here's our plus and minus. wiggle in the middle. So this is going to be our A phase. Here's the B phase connector, and here's the C phase. So this will be VAB, BBC, and up here will be BCA. Let me put that on the outside, actually. Like that. All right. So our definitions of what a phase voltage is, what a line voltage is, what a phase current is, and what a line current is, do not change depending on how things are connected, okay? So a phase voltage is always just the voltage drop across one phase. The line voltage is always just the voltage drop between the transmission line terminals. So with that in mind, what are our phase voltages for this system? What's the voltage drop across one phase? It's the source voltage. It's the exact same thing that it was, right? It's just now we're using VAB, VBC, and VCA, okay? So our phase voltages for our sources are always just going to be the voltage provided by our voltage sources. So VAB, VBC, and VCA. Now, line voltages are defined to be the voltage drop that appears across the transmission line terminals. So here I have a pair of transmission line terminals. So I should have some voltage VAB. Here I have another pair of transmission line terminals. So this will be VBC. And across these transmission line terminals, I'll have VCA. Let me draw them over here as well. So our line voltages in a delta connected source, and we'll see it in a delta connected load here in I guess several minutes, but that'll be okay, are literally the exact same quantities. So this is where things start to get weird and confusing, because previously with our Y connected source, the line voltages and the phase voltages were very different things. Here in a delta connected source, they are literally referencing the exact same quantity, okay? So us having a fundamental understanding of what these quantities are is what makes this so damn different. For our phase currents, once again, I'm going to define my phase currents as the currents that are flowing into the positive polarity terminal of each of our voltage sources here. So this is going to be IAB. Here's IBC. And here's ICA. And I'll try to represent them here. Like so. All right, so we've finished what the different quantities are for our delta connected source. So before we move on to loads, I think I have enough time to entertain a few more pertinent questions, if there are any. So hit me with pertinent questions if there are any. AB. Very pertinent question. So just for a heads up, double subscript notation is always going to be what node it starts from is the first subscript, what node it's flowing to is the second subscript. So that current is flowing from node A to node B, so it'll be IAB. Any other questions before we move along to the load side of things? All right. So these are the only permutations of how we can connect a three-phase voltage source. It's either going to be in a Y connection or a delta connection. It's the exact same thing for loads. It's either going to be in a delta or a Y. So we're going to talk about Y connected loads first. Later, hey, so by the end of the quarter, it will be, I think, Dr. Hall's problem. I think he's got the class after us. Didn't want to get out of bed because it was raining too. All right. So my screen will stop flashing and disconnect to the damn projector. There we go. All right, so similar thing. So this is going to be impedance ZYA. Here will be impedance ZYB, and here will be impedance ZYC. We may also have a neutral conductor. So here's our classical representation, which again, I hate with a passion. Here is our modern representation. Here's A, B, C, and N. Okay. So that's how we'll draw things. Either one or the other of them. My money is always going to be the one on the right. Once again, our definition for phase voltages has not changed. So we're just looking for the voltage drop across one phase of our load. So that's going to be this voltage, the capital A, capital N for the A phase, the BN for the B phase, and VCN for the C phase. I'm going to go ahead and draw them on my modern representation over here. Like so. For my line voltages, once again, those are just the voltage measured across my transmission line terminals. So we're going to have VAB, VBC, and VCA. Effectively, what we're going to have is the exact same thing as we had for a Y-connected source, but we're going to use capital letters for all of our subscripts instead of lowercase letters because we're on the load side of the system. And now for our phase currents. IAN, IBN, ICN, like so. And let me write those down. So once again, here, nothing more than what we saw with our voltage source, just moving over to the load side of things. Sure. And let me know if you can't read my city penmanship. Anybody have any questions about the Y-connected load? Go for it. So we're not putting the line currents in because the line currents are the currents that flow down our transmission line. Because I don't have a transmission line connected, which is why I'm not representing a line current here. So we're only going to see line currents effectively in a full system where we have a source transferring energy to a load. And we're just looking at the load by itself, effectively disconnected from everything. We have no transmission line for the current to flow through. Right, which is why I drew the line currents there, because we had a full completed system. So when we start our analysis, which will be kind of the first thing that we're doing on Thursday, because I think today is Tuesday, we are going to be looking at what the line currents are and actually throwing math at that to sort out how the whole system as a whole works. Yeah. So just a three-phase voltage source or a three-phase load by itself, that's boring. We want to look at a system as a whole. All right, so let's wrap things up by talking about delta connected loads. And then okay. So for our delta connected loads, it's going to look very similar to a delta connected source, except that I'm just going to put my transmission line terminals on the opposite side. So here's going to be A, here's B. So this will be Z delta A. Over here will be my C terminal. Z delta B. Z delta C. Let this guy go up here. like so. And now V delta A between A and B, V delta B between B and C, and Z delta C between C and A. So what do you guys think our phase voltages are going to be? The same thing as, okay. Yeah, no, so it won't be the same thing as what we just did because that was Y connected. So by definition, our phase voltage is just the voltage drop across a single phase of our source or load, right? So the impedance Z delta A is one phase of our load. So the voltage drop that we're looking at there should be between the A and the B nodes, right? So we're going to call that guy VAB. So that would be this voltage on the classical representation, or this voltage on the modern representation. Looking at our impedance Z delta B, we would have a voltage drop that is VBC. And looking at our C phase, we would have VCA. So our line voltages, once again, always determined by just looking at the voltage drops between our transmission line terminals. So here I have an A terminal and a B terminal, so this is VAB, and this is the exact same VAB. Here is VBC, and the same VBC on the modern representation. And lastly, potential between transmission line terminals C and A, which is just VCA like so. So once again, we see that our phase voltages and line voltages are the same thing for a delta connected load. Lastly, we have our phase currents. So that's just the current flowing into the positive polarity terminal. That's going to be IAB, IBC, and ICA like so. All right, so we've got a little over 10 minutes left, so I'm going to call it quiz you, but this isn't for a grade or anything like this. I'm just going to draw a system, and I want you to identify things. So Bless you. All right, so the first thing that I want you guys to tell me is what type of source we have here. Is this a Y-connected source or a delta-connected source? It is a Y-connected source, okay? So we're gonna call this a Y something system. Is the load a delta-connected system or a Y-connected system? It is a delta, because we're seeing the impedances are between the transmission line terminals without reference to a neutral. So it's delta. So this is an example of a Y delta system. Okay? So the first thing is the source, how the source is connected. The second thing is how the load is connected. So this is a Y delta system. Okay, so this current that I've just drawn right here, IAB, is that a line current or a phase current? Why is it a phase current? So it's a phase current because it's flowing through one phase of the load, okay? What about this current, ICC? That's a line current because it's flowing through the transmission line. Absolutely correct, right? What about this voltage VAB? So that is a line voltage because it's measured between the transmission line terminals of the source. What about this voltage VBC? It's both. It's a line voltage and a phase voltage because it's delta connected, and the line voltages and the phase voltages are literally the same for a delta connected thing. Okay. So you were both right. This is why it gets difficult. So having a fundamental understanding of what all of those definitions means will tell you what I'm looking for. Because when I give you a problem, I'm not going to say find VAB, VBC, all that kind of stuff. I'm going to say find the line voltages at the source, find the phase currents in the load, all of that kind of good stuff, because that's what you're going to be asked to do. So having some fundamental understanding about how these definitions are applied to tell you which quantities you're looking for is absolutely critical to you successfully navigating this portion of the class. Okay. I understand it is not easy. I also understand that it is new. I hope I have made it obvious that I am willing to answer questions. So if something is not clear, please ask. All right, so that's all I have for us today. On Thursday, we're going to start looking at analyzing systems. This was largely definition, like it's not even theory to me, I guess.
Yeah.
Depends on what you feel is theory, but yeah. So. All right, thank you guys.